So, good evening. Welcome back. Okay, Saad, Sameer, Vasant, Yash, Rishi, Harsh, Aryan. Good evening to all. Okay, Ashish, Swati. Good evening. Okay, so question number 3 of alcohol phenol ether. In the last lecture we have completed question number 1 and 2. Okay, they are related to IUPAC names and structures. Okay, now draw the structures of all isomeric alcohols of molecular formula C5H12O. That means this question is related to isomerism. Okay, so how many carbons are there? 5. Okay, so as carbon are 5 and C5H11OH, because we have to write isomeric alcohols. So if they are alcohols, there should be one OH. So C5H11OH means OH is added. That implies it is obtained from C5H12. Means this is the pentane. Its hydrogen is replaced by OH and we get C5H11OH, right? So our parent chain is pentane, C5H12. So first of all we start from C5H12. So if we have 5 carbons, they are arranged like this, or like this, or third these are the 3 structures of pentane: normal pentane, isopentane and neopentane. Is it visible? Yes. Okay, Harshil, Sahil, Praharsh and Charitra. Okay, good. So see, CH3, CH2, 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 CH3. Here CH3, CH, CH3, CH2, CH3, 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 CH3 and CH3. Right? So these are 3 pentanes. Now from these pentanes, we will identify type of carbons and hydrogens. Primary carbon, secondary carbon, secondary carbon, secondary, primary. In this case, primary, tertiary, secondary, primary, primary. Here primary, 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 quaternary. So actually hydrogen is replaced by OH. That means number of alcohols is equal to number of different types of hydrogens present in these structural isomers of pentane. See, in pentane we have to replace H by OH. That's why number of alcohols is equal to number of different types of hydrogens. Number of alcohols is equal to number of different types of hydrogens present in different structural formulas, structural isomers of pentane. So now tell me, how many types of hydrogens are present in normal pentane? This is normal pentane. So how many types of hydrogens are present in this case? Yes. In normal pentane, how many types of hydrogens are present? Only two? Vasant, you are wrong. Anyone else? See the environment as well. You know primary and secondary. But you know this secondary and this one, are they same? Ashish, Harshil, very good. Swati, great. There are three types of hydrogens. One type of primary and two types of secondary. In normal pentane, we have three types of hydrogens. And that's why there are three types of alcohols. In normal pentane, we have three types of alcohols. What about this? In isopentane, means three types of alcohols are formed. Okay, and what about isopentane? In isopentane, how many types of hydrogens are there? Very good, Yash, right. In isopentane, tell me, how many types of hydrogens are there? Sahil, wrong. Harshil, very good. 4, again 4. Say, these primary are attached to tertiary and this primary is attached to secondary. So, two types of primary, one type of secondary, one type of tertiary. So, total 4 types of hydrogens are there. So, 4 isomers are possible for isopentane. Very good. Great, Sidhu. Sahil, good. Yash, Swati, great. Okay. What about neopentane? In neopentane, how many types of hydrogens are there? Hydrogens, keep in mind. In neopentane, Saad, wrong. Hydrogens, beta, not carbon. Is there carbon with quaternary? Is there hydrogen with quaternary carbon? Very good. Sahil, Harsh, Swati, good. 1. So 1 isomer is possible for neopentane. 1 alcohol is formed by neopentane. So total 3 plus 4 plus 1. 8 isomeric alcohols are formed by C5H12O molecular formula. So first we go to the basic of C5H12O, it is isomer of pentane. It is obtained from pentane, and from normal pentane we get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. So first of all we attach CH3, CH2, 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 CH2 and OH. Okay, then CH3, CH2, CH2, CH, OH, CH3, then CH3, CH2, CH, OH, CH2, CH3. So these are the three isomers obtained from normal pentane. One of the hydrogen, different types of hydrogen. See, primary hydrogen are same. These two secondary hydrogens are same, but this secondary is different. These secondary are attached from one side by primary, other side by secondary. But this one is attached to secondary carbons on both sides. That's why there are three types of hydrogens and three types of alcohols possible. This is primary alcohol and these are secondary alcohol. This is pentane 1-ol, pentane 2-ol, pentane 3-ol. See, 1, 2, 3. 1, 2, 3, 4, 5. Means 2-ol, 1, 2, 3, 4, 5. So 1-ol. So pentane 1-ol, pentane 2-ol, pentane 1-ol, pentane 2-ol and pentane 3-ol. See, E is removed because it starts from O. Okay, so these are the three isomers, and first one is primary, second is secondary, third is also secondary. So first three isomers, and classified isomers of alcohols in question 1 as primary, secondary, tertiary. So we have classified accordingly. Now come to isopentane. So say in isopentane we have primary, secondary, tertiary, and both the primary are same. These primary are same, but this primary is different because this primary carbon is attached to secondary carbon, but these primary carbons are attached to tertiary carbon. That's why there are two types of primary and secondary, tertiary. Okay, so let us draw structures. CH3, CH, CH3, CH2, CH2H, then CH3, CH, CH3, CH, OH, CH3, then CH3, COH, CH3, CH2, CH3, and last one, let us draw from this only, OH. So these are the four isomers obtained from isopentane. Okay, just name them. This one is, see, 1, 2, 3, 4. So 3 methyl butane 1-ol, right? And what about this? 1, 2, 3, 4. 3 methyl This one, 1, 2, 3, 4. OH should get lowest number. Here OH, if we start numbering from this side, OH will get lowest number. In this case, if we start numbering from left side, then it gets lowest number. So we start from this side. Okay, so it is 2-methyl butane 2-ol. Okay. Now, what about this? See, 1, 2, 3, 4. So it is 2-methyl butane 1-ol. Right? So these are structures obtained from isobutane. This one is primary, this one secondary, this one tertiary, and this one primary. You can say the carbon attached to OH, primary, primary, secondary, tertiary. Now neopentane, only one isomer is possible. Just write like this. Okay, so name of this compound. First write the name of this compound. Yes, what is the name of this particular compound? Good evening, Varun. What is the name of this compound? First, name this compound, and is it primary, secondary, tertiary? 2,2-dimethyl propane. Note up. 1, 2, 3. 2, 2 dimethyl propane 1-ol. Okay. Very good sign. It is primary alcohol. Keep in mind. Sometimes students are confused because of this thing. That this is quaternary carbon. Obviously, this is quaternary, but the carbon to which OH is attached is primary. Right? That's why it is called primary alcohol. Good, Swati, good. 2,2-dimethyl propane 1-ol. Very good, all of you. Great. Okay, so this is the question number 3 of alcohols, phenols and ethers. Now question number 4. Today I am on DL. I went to civil hospital. Okay, that's why. Okay. Okay, question number 11.4. Explain why propanol has higher boiling point than that of hydrocarbon, butane. So you have to answer why propanol has higher boiling point than that of hydrocarbon, butane. Very simple question. Just answer it fast. Very good. Harsh, Sahil, great. It is due to intermolecular hydrogen bonding that is present in propanol and is absent in hydrocarbon, butane. Very good. So you should write propanol C3H7OH OH C3H7 like this. Propanol is associated, propanol molecules are, you can write propanol molecules are associated through intermolecular hydrogen bonding due to the presence of OH group. That's why it has higher boiling point than that of butane, which has weak van der Waals attraction. Weak van der Waals attraction. Okay. And you know intermolecular hydrogen bonding is very strong, strongest among molecules, and that's why their boiling point is higher than that of hydrocarbons. Very simple question. Very good. Harshil, good. Hydrogen bonding and butane, there is van der Waals attraction. Okay, so this is 11.4. Now 11.5. Alcohols are comparatively comparatively more soluble in water than hydrocarbon of comparable molecular masses. Explain this fact. Yes, I think you can answer it easily. Yes, tell me. Great. That's it. Because alcohols, due to the presence of OH, alcohols can form hydrogen bond with water. Alcohols can form hydrogen bond with water. Okay, but hydrocarbons, they don't have such polar group, so they will not form hydrogen bond with water, or even cannot break hydrogen bonding in water. So even they form a separate layer, they cannot enter into water. You know, when oil is there in water, oil forms separate layer from the water, because oil, in oil there are van der Waals attractions. In alcohol, sorry, in water there is hydrogen bonding. Hydrogen bonding in water is very strong. So these van der Waals attraction cannot break hydrogen bonding and can enter in it. Okay, so they will not enter into water even. Okay, that's it. Very good. So we'll write alcohols can form hydrogen bond with water and can break H bonding of water to enter into it. That's why alcohols are soluble in water, but hydrocarbons neither form H bond with water, nor they break H bond between water molecules. Okay, so they are least soluble or even insoluble in water. Done? Great. Now 11.6. It is what is meant by hydroboration-oxidation, hydroboration hydroboration, oxidation reaction illustrate with an example. We have already done it in the text part. We have covered it in the text part completely. If you would like, I will write once again. What do you say? Do you want me to write once again? Good, Setu. No. Now tell me, what do you want? Do you want me to write it once again? No. Okay, she said no. What about others? Okay, tell me, what is hydroboration actually? Like hydration. Hydration is addition of water. Hydrohalogenation, addition of hydrogen and halogen. Hydrobromination, addition of hydrogen and bromine. Bromination, addition of bromine. Halogenation, addition of halogen. Just like that, what is hydroboration? Yes, what is hydroboration? Very good. It is addition of hydrogen and boron. Like if we have CH3, CH double bond CH2, now BH3, actually B2H6 in the form of BH3 is added in it, in THF or dry ether. So we get CH3, CH2, CH2 and BH2, means one H and one Br. One H and one BH2. In BH3, H and BH2 are added like this. So, means one hydrogen is replaced by CH3, CH2, CH2. Same, two more propene can be added. So we get CH3, CH2, CH2, thrice B, tripropyl borane. We get tripropyl borane. Okay, after that we add H2O2, means in the alkaline medium, hydrogen peroxide, alkaline hydrogen peroxide. Okay, so we get 3 molecules of CH3, CH2, CH2OH plus H3BO3. That's it. This is hydroboration oxidation. First is hydroboration and then it is oxidation. And it seems like anti-Markovnikov addition of water, but it is not true. There is no violation of Markovnikov rule. Markovnikov rule is applied, but it seems like product formed is like anti-Markovnikov addition of water. H plus and OH negative. OH negative is added to the side where more number of hydrogens are there. Okay, so it seems like anti-Markovnikov addition. Okay, without rearrangement. There is no rearrangement because in that case I have drawn all the things. Even mechanism is given, so you can go through the text if you don't know. Okay. Okay, so this is 11.6 question number. Now 11.7. Question number 11.7. Give the structures. Give the structures and IUPAC names of monohydric phenols of molecular formula C7H8O. Give the structures and IUPAC names of monohydric phenols. Only monohydric. What do you mean by monohydric? One OH. As there is only one oxygen, so it should be monohydric. Okay. So monohydric phenols, formula is this. So say, first of all, if we draw this structure, it is C6H6. Now one of the hydrogen is placed by OH, so it becomes say C6H6. Okay, one hydrogen is placed and OH is added, so it becomes C6H5OH. C6H5OH means C6H6O. So what is left? We have to add to become C7. One carbon is there. C7H8. So CH2O. Okay. That means one of the hydrogen is removed and CH3 is added. Right? First of all, we have C6H6. This is the case. C6H6. Because in this case, it is phenol actually. So phenol is C6H6O. So one of the hydrogen is replaced. So it is C6H5O. So we have to add CH3 to get this. So CH3 may be at position 2 or CH3 may be at position 3 or at position 4. So these are the structures. What are their names? Write the names. Very good, Sahil. Great. They are Setu. I think you are asking for the last one in case of hydroboration-oxidation. Sorry, I didn't see your message earlier. Okay. So they are, it is 1, 2, 1, 2, 3, 1, 2, 3, 4. So it is 2-methyl phenol. This is 3-methyl phenol and 4-methyl phenol. Or common names are orthocresol, metacresol and paracresol. Right? Okay, 11.7. Now 11.8. While separating a mixture of ortho and para nitrophenols by steam distillation name the isomer which will be steam volatile. Give reasons. Yes. So tell me, what is the reason? Okay. Very good. It is orthonitrophenol, Harshil. Chelation, intramolecular hydrogen bonding. You know all. Very good. Ashish, very good. Means, say this is the orthonitrophenol. This is orthonitrophenol. And this is paranitrophenol. So in orthonitrophenol, you know, this H plus from OH and O negative from nitro, they can form intramolecular hydrogen bonding. Intramolecular hydrogen bonding means hydrogen bonding is formed between two polar groups belongs to the same molecule. So because of this intramolecular H bonding, it becomes inert. It is not interacting with other molecules, and therefore, and this type of structure, a ring structure, see, 1, 2, 3, 4, 5, 6, 6-membered ring is formed. Such is called chelation. Ring structures formed by intramolecular hydrogen bonding. Due to that, this is called chelation, or this is chelate. Okay, and due to chelation, they have low boiling point. So orthonitrophenol becomes steam volatile. But in case of paranitrophenol, so there is intermolecular hydrogen bonding. There is intermolecular hydrogen bonding, and due to intermolecular hydrogen bonding, its boiling point is high. It has high boiling point, and that's why it is steam non-volatile. It is associated through, molecules are associated through intermolecular hydrogen bonding, and that's why they are steam non-volatile. So in this way we can separate orthonitrophenol and paranitrophenol by steam distillation, in which orthonitrophenol goes with the steam and paranitrophenol remains behind. That's it. Okay. Now next is Question number 11.9. Give the equation equations of reactions of preparation of phenol from cumene. Yes, that we have done already. Just tell me the conditions. Just write the conditions, please. Write the conditions. Second question is also belong to the same preparation of phenol. Write the chemical reaction. Write the chemical reaction for the preparation of phenol. For the preparation of phenol from chlorobenzene. Yes. What are the conditions? Fast, write fast. Okay. Now is it okay? Okay, first with cumene. So you know what is cumene? Tell me what is cumene? What is the name of cumene? Cumene, what is cumene? What is IUPAC name or common name, whatever you know? Tell me. Very good. It is isopropyl benzene. So cumene is isopropyl benzene. Cumene is isopropyl benzene, right? So in isopropyl benzene, this is isopropyl benzene. So aerial oxidation takes place. O2, right? In the presence of O2 at 368 to 408 Kelvin. If you don't want to write, just skip the temperature if you don't know. If you know, if you remember the value, just write in the reaction. Okay? And this is called aerial oxidation. So in the aerial oxidation, we get this CH will allow O2 to add, and we get cumene hydroperoxide. Okay? You have written it very good. Cumene hydroperoxide, and then in the presence of hydrolysis, which on hydrolysis will dilute H2SO4 at 323 to 363 Kelvin, we get phenol along with acetone as the side product. Acetone along with phenol. So this is cumene process. This is also known as cumene process. Okay, this is first one. Then is it, can I write here? Okay, I will erase it. Okay, so this is the first part, that from phenol preparation from cumene. Now second one, chlorobenzene preparation of phenol from chlorobenzene. So this is chlorobenzene. So you know, in chlorobenzene, CCl bond acquire double bond character. It is very difficult to break this bond. That's why NaOH addition takes place what under vigorous condition. We need very high temperature of the order of 623 Kelvin temperature and 320 atmosphere pressure. These are not normal conditions. Vigorous conditions are required because CCl bond acquire double bond character, and that's why we get sodium phenoxide. First of all, we get sodium phenoxide, and the sodium phenoxide on hydrolysis we get phenol. That's it, right? Any doubt up to this? Any doubt? Just with dilute HCl we get phenol, NaCl is removed. Okay, here water is removed because O and A is attached here. Okay, and NaCl and water are removed. There are two molecules of used, so is minus NaCl and minus water. Okay, so we get sodium phenoxide and ultimately we get phenol, right? Okay, she said there is no doubt up to this. Okay, so that's all for the day. Thank you. We have completed up to 10th question. We will start from question 11 onwards tomorrow. Okay, bye bye. Okay, good night. साहिब, हाँ विदा लेने का समय आ गया है. ओके, कोई नहीं, कल फिर मिलेंगे, ज़्यादा देर नहीं है. ठीक है, ओनली 24 आवर्स, नॉट 24 आवर्स, 23 आवर्स.